So let's go do the EC analysis. So in EC, let's now use another color. So let's remove these illustrations since we did it for DC. Okay, so let's do another color, green for example. So in EC, the capacitors are short. So this guy will be shorted, this guy will be shorted, this guy will be shorted. So RE will in EC will not be counted because it's just 0. Again, this one here will be shorted. What else? And this also will be shorted. So now both stages are connected, not like DC. And this is also shorted here. What else? Then we cancel DC sources. So we'll cancel VCC. So VCC will be just a ground. And now let's draw the AC equivalent circuit. So number 2. The AC analysis. We start by the 2 transistors. So for transistor 1 we have R pi like this, and we have beta IB1. Here is R pi. Remember, R by 1 equal to R by 2. So we'll just call them R pi because IB here is IB here. So VT over IB is equal to VT over IB. So both R pi's are equivalent. So we'll just call it R pi. Here is IB1. Here is B1, C1, E1 for transistor 1. And here is the other transistor. Beta IB2, R pi, IB2. Now let's connect the other parts of the circuit. So let's start by base 1. So base 1, here is base 1. Between base 1 and the ground, we have R1, we have R2. Actually, R1 and R2 are parallel now because in EC, parallel means they are connected with 2 same terminals, terminal 1 and terminal 2. So they are connected with the same terminal here and also the same terminal, which is the ground, the other terminal. So we have here R1 parallel R2. What else? Also, B1 is connected to R signal and V signal. And that's it for base 1. Now let's connect emitter 1. So here is the emitter of the first transistor. And as you see, because we shorted R2, it's connected to ground directly. So it's connected to ground here. That's good. Now collector 1. So between collector 1 and the ground, remember VCC now is grounded, we have RC. And C1 or collector 1 is connected to base 1. So here is base, I'm sorry, base 2, I'm sorry. Okay, so this is the equivalent circuit of the second transistor. Here is base 2, here is C2, here is E2. And C1 is connected to base 1. Now let's go to the second transistor. So let's start with the base. So between the base and the ground, we have these two transistors, R1 and R2. And remember now also R1 and R2 are in parallel because they are connected to the same start or same first terminal and same second terminal, which is the ground. So between base 2 and the ground, we have R1 again parallel R2. R1 of the second circuit parallel to R2 of the second circuit. Now emitter 2, nothing else with base 2. Now emitter 2, again emitter 2 is also connected to ground now in AC because the capacitor will short RE, so RE2 or the emitter 2 will be connected to ground. And that's it for E2. Now C2. Between C2 and the ground, we have RC. And we also have this branch, which is RL. And that's it. So this is, the total circuit. Yeah, it's long, but again, when we go into the analysis now, we'll find that it's easy. Before we continue, let's mark the important points in our circuit. First, where is the input? Here is the input. And now since you have two stages, make it the input 1. And here is our input of the whole circuit, which is our input 1 at the same time. And the V input 1 is actually the input of the whole circuit at the same time. Where is the output 1? The output 1 is between collector 1 and the ground. So here is the output 1. Where is the input 2? It is the voltage at base 2. So here is, and the base 2, by the way, is connected to collector 1. So here is the input 2, which happens to be the same as the output 1. And where is the output 2? It's the voltage across the resistor RL, or the load resistance, or RC, because they are in parallel. So this is VO2, which happens to be the same as the main output of the circuit, VO. And if we are interested, where is our input 2? Our input 2 is between the terminals of the input 2. So it should be here, looking at that, but we don't need it in that particular, unless, of course, the question asked for it. So let's analyze now the AC. And when we say analyze AC, I mean we found our input, we find our output, we find V naught, EV, and GV. Main stuff. So let's start by, okay, let's take it to another, let's copy and paste this. So our input, number 1, our input equal to, so when we look here, okay, remember this portion of the circuit is isolated from that portion, and from that portion as well. So the 3 portions are isolated, okay? So basically, just by looking into the circuit here, you find that our input is actually equal to R1 parallel R2 parallel R bar. if you want to do it, you know, in details, you can say it's equal to R1 parallel R2 parallel the resistance seen after R1 parallel R2. Let's call it R input dash. So this is equal to R1, R2, and what is R input dash? So the voltage between these 2 points, this point and the ground, which happens to be the input 1. Over the current, which is IB1. R1, R2. The input 1 is actually the voltage of R pi, which is IB1 R pi. And the current is IB1. So again, we get to the same conclusion. R1, R2, R pi in parallel. Good. Let's calculate calculate this value. This is 100 kilo parallel 47 kilo parallel with 489 kilo ohms. So this will reduce to 424 kilo ohms. Number 2, RO. RO is resistance seen by the load. So we look in that direction. And when we do that, we should cancel the source. It's an independent source. And in that case, it's V signal. So we're going to short V signal. So when you short V signal, what's going to happen here is that IB1 in that circuit, the source that provides this IB1 is shorted. So IB1 will be 0. So beta IB1 is also 0. So IB2 will be also 0 because it's the same, you know, in this middle circuit in here. There is no source to feed it. So beta IB2 again 0 or open circuit. So you will end up that RO is equal to RC. And RC is 6.8 kilo ohms. It's pretty high. Look, we said that a good circuit should have low output resistance, high input resistance. If you look here, you know, the output resistance is actually higher than the input resistance. So till this moment, we doubt where is the advantage of having 2 stages, but we will get to it now. Number 3, AV. Let's also make it, you know, AV for stage 1, then AV for stage 2. So let's start by AV1. AV1 is equal to VO1 over the input 1. Okay. So here is the output 1. The voltage across either this resistance or, or this resistance, R1 parallel R2, or this resistance, R pi, because all the 3 resistances are in parallel, right? So we can say that VO1 is equal to, since the current that is coming out of these 3 branches is added up. So if we assume that we have 3 currents flowing like this, so these 3 currents will add up to beta IB. Beta IB1, which is the current in that current source. But this current is flowing from bottom to up, so the voltage is positive, negative, opposite to V output 1. So minus beta IB1 RC parallel R 1 parallel R2 parallel R bar. And what is V input 1? V input 1 is the voltage across R1 parallel R2 or bar by, which is actually IB1 R bar. So EV1 equal to minus beta IB RC parallel R1 parallel R2 parallel R by over IB1 R by IB1. I'm sorry, this is IB1 as well. IB1 will go with IB1, so we'll end up with minus beta RC parallel R1 parallel R2 parallel R by over R by. So we can calculate it as well. So if we calculate this value, this term, we find that EV1 is equal to minus 53.37. Good. Number 4, AV2. So stage 1 will give us amplification of 53. Stage 2, VO2 over V input 2. Let's go back to the circuit to check that. So here is VO2, the voltage across RL or RC, or the parallel combination of them. So the parallel combination of RL and RC has a current flowing from bottom to up, which is beta IB2. So VO2 equal to minus beta IB2, and the parallel combination of RL parallel, or let's write it in that way, RC parallel RL. And V input, V input 2 is the voltage across R by or R1 parallel R2 or RC. In a specific R by, we know the current flowing through it, which is IB2. So IB2 R by. This is the voltage. IB2 R by. Now if we compensate, V output 2 minus beta IB2 RC parallel RL over IB2 R by. IB2 will go with IB2. So we end up with minus beta RC RL over R bar. Good. Number 5, the total gain. This should be VO over VN. Remember, VO is actually VO2. And VN is actually V input 1. Let's multiply and divide by V input 2. We didn't do anything. This is equal to VO2 over V input 2, V input 2 over V input 1. Again, we didn't do anything. But remember, V input 2 is actually equal to V output 1. So we can write this again as first term is the same, V output 2 over V input 2, but I will replace V input 2 here by V output 1. And what is this? This is AV2. Look, AV2. And what is this? This is AV1. AV1. Which we did already calculated, right? So AV equal to AV1 multiplied by AV2, so equal to AV1 minus 53.37. AV2 is, we didn't calculate, I'm sorry. So we can calculate this value, and it will be minus 31.69. I'm very sorry for this. So AV2 is minus 31.669. So that will be a massive number, 1691.29. And here is the advantage of using multi-stage amplifier. Okay, so our input was the same, exactly the same. Our output was exactly the same as common emitter. But now we know that common emitter usually have amplification from tens to a few hundreds. Now we have thousands, 1,600. So, and also we get rid of the phase shift because minus multiplied by minus become positive. So we get also rid of the phase shift that we have with the common emitter amplifier. Although it's not a big problem. You know? So the advantage of this circuit is to have very high amplification. Amplifications that you may not be able to produce with only one stage. And for all amplifiers, you know, for all multi-stage amplifiers, usually the gain is a multiplication factors. The gain of the first stage multiplied by the gain of the second stage, and so on. Why? Because of this relation here. You know, this trick that we did is always valid for any kind of multi-stage amplifier. Number 6, and finally, GV. GV is equal to AV, our input plus our signal. So AV is 1691.29. Our input we calculated, it was, let me go up. It was how much? It was, 4.24 kilo ohms. 4.24 kilo ohms. And I'm sorry I didn't mention how much is our signal. So our signal, let me do it in the last slide. So our signal here is 5 kilo ohms. 5 kilo ohms. Is 5, so this will be around half. Okay, so 776. Okay, so this is the first example about multi-stage amplifiers. Okay, and we see here that when we cascaded two common emitter together, the amplification become massive, very big. Okay.